All right, the paired t-test. So we call it a paired t-test, although mechanically in our calculator we're just doing a one sample t-test. But this is what n will be for phantom. When the conditions are met, we are ready to test whether the paired differences differ significantly from 0. We test the hypothesis with mu d. So mu d is going to be our parameter. This is going to be our parameter of interest now, and that d stands for the differences. So this would be the mean difference, where we have the mean of this group and the mean of that group. This will be the mean difference of, and then whatever we're talking about. The null is mu d is equal to delta naught, where once again delta naught is almost always 0. So typically your null is mu d equals 0. And then your alternative is less than, greater than, etc. We use the statistic. We're still talking about a t because we're talking about means with degrees of freedom equal to, and since we're doing really just a one sample, because that's all we really have is one sample of differences, or degrees of freedom is n minus 1 again. This time we take the mean of our differences, we subtract that null, which is usually 0, and we divide it by the standard deviation or standard error that we usually have for the differences, a one sample mean. So that standard error is going to be equal to the S of the differences divided by the square root of n. That's our same formula. It's supposed to be sigma over square root of n, but this time it's S. So this is not really on your formula sheet because it's really just for one sample. This is the formula on your formula sheet for one sample where it's supposed to be sigma over square root of n, but we're going to use S in place of sigma. That's why we use a T model, and there's no two samples, it's just one. So we don't have two of those that we're trying to add together. If you don't already have this data in your calculator, please pause the video and put it in your calculator. Lake County, Illinois Health Department experimented with a flexible 4-day work week. For a year, the department recorded the mileage driven by 11 field workers on an ordinary 5-day work week. Then it changed to a flexible 4-day work week and recorded the mileage for another year. So it's the same people over a 2-year time period. They've got Jeff's mileage on a 5-day work week and Jeff's mileage on a 4-day work week. So the idea is that you have to go to the same places just over 4 days. I guess you would have maybe less time having to go like from the warehouse out into the community and back. Well, you don't have that as often when you only do it 4 days because you're just you can maybe do places that are close together on the same day and things like that. So is there evidence that a 4-day work week would change how many miles workers drive? So that's indication of a two-tailed test. Nothing in this problem no one's saying, oh, I'm paired. It's not like flashing at you in the words. You need to pick up on the fact that this is paired data, that this is Jeff's mileage for 5 days and Jeff mileage for 4 days, etc., etc. So you need to be aware that it is a paired test and conduct a paired test. That's probably the hardest part, is not doing a two-sample t-test. So my parameter is mu d this time, and this would be the mean of the difference in mileage. Now I like to indicate which way I am subtracting, so it doesn't matter, but whichever way you subtract, stick with that throughout the problem. So I'm just going to do 5-day minus 4-day, just because that's first and that's second. All right, the null, that's P. The null is that difference is 0, that there really is no difference. The alternative, because they just want to know a change in, would be the difference is something other than 0. I don't know if it's greater than or less than. That wasn't indicated to me. It's just, is there a difference? All right, your assumptions in conditions. I do need some sort of randomization. I don't see that I have any randomization. So I'm going to go ahead and write the data is not said to be random. But hopefully these miles are independent and representative. All right, and then for the nearly normal condition, make sure you have this data in your calculator under Stat Edit. We are not looking at histograms of the two individual pieces of data. That would be for 2 sample t-tests. We're only interested in the differences. So what we're going to do is once you have the data in L1, L2, you go and put your cursor way up on top of L3 and you type L1, which is second one, minus L2. That's the way I chose to subtract in the problem, 5 minus 4. So it's written down here at the bottom, L1 minus L2, and I press enter. And now I get the pairwise differences. I get the difference in the mileage, 5-day minus 4-day. This is what I'm interested in. So now you can see some of the differences are big, some of the differences are negative and smaller. Okay? So what I'm interested in is this list. I don't even need these two lists anymore. I could delete them out of my calculator if I wanted to. So we're going to make a histogram of L3. That's the list I'm now interested in examining. So zoom 9. And once again, I see a little bit of skewness, nothing too crazy. So I'm going to come over here and draw that histogram. That is, in fact, the y-axis because some of my differences are negative. Press trace. We got negative 467, positive 427.25, 1321.5, 2215.75, 3110, and 4004.25. So now I'm going to go ahead and write the distribution of differences. Is not extremely skewed. And the central limit theorem says we can proceed with the T model. All right, so we are now going to do a paired t-test. I'm going to let the calculator do this work for me. I'm going to go to Stat Test. There is no paired t-test in the calculator. It's just mechanically a t-test. We don't call it that, but that's what we actually just do, is a t-test. The data is in my calculator. I don't have the stats. I have the data. The null, mu d, equal to 0. I'm going to make that a 0. My data is in L3, not in L1. It's a two-tailed test. I'm going to press calculate. I'm going to draw out some of this information. It's T, sample size is 11, so this is a T10 model. So T10 equals 2.86. 2 times the probability of T10 being greater than 2.86 is 0.017. I could draw that model out as well. This is a T10 model. 2.86 on each ends. That's what I found the probability of. It's probably I should have made it go a little further out than that because this is only 1.7%, but that's okay. The sample mean, by the way, was 982, so not very close to 0 at all. Remember, the standard deviation that's the standard deviation of the sample. The standard deviation of this model would be that divided by the square root of 11. So a little bit smaller than S. All right, so I'll follow up with the p-value of 0.017 is smaller than alpha of 0.05. I reject the null, which leads me to conclude that there is evidence of a difference in the miles driven for each work week, and we can follow that up with which way that difference goes. Since my mean was positive and my test statistic was positive and I did 5-day minus 4-day, then I'm concluding that outcome would be a positive outcome, meaning the 5-day is more. So in fact, it seems they drive more miles on a 5-day work week. So we could conclude pretty confidently that you'll save some mileage on the 4-day work week over the 5-day work week. And that is a paired t-test.